Hello, everyone, and welcome to Physics 212. This is Lab 11, which is on energy momentum studies. And in particular, we're going to look at the ballistic pendulum. So this experiment is going to involve two really important principles. One is the conservation of linear momentum, and the other is the conservation of mechanical energy. So again, the video that follows was recorded initially during the pandemic. So you notice that the lab numbering is different. I believe I called it lab 6 when I originally recorded this. And also the question numbering is a little bit different. I kind of combined questions together, but essentially it's the same exact questions. It's definitely the same exact information. Okay, so you have all the information that you'll need in that video to do this lab, but if you're actually doing the lab this semester, lab 11, you want to make sure that you answer questions 1 through 17 from the lab manual. And this is basically it's lab 9 in your lab manual. It's the first part of lab 9. Okay, so make sure, again, that you answer questions 1 through 17. So they're essentially the same as the following video, but they don't match up exactly. The other thing is you'll notice that in the video that there is data. And again, that's because it was during the pandemic when we couldn't actually collect data ourselves. So if you're making up this lab, if you're watching this because you're making up lab 11, you can either use the data that's in the following video if you'd like, or you could just use your lab partner's data from this semester. Okay, so with that in mind, let's go to the actual video for this lab. Hello, everyone. Welcome to Physics 212, Lab 6. So this lab is going to be on a piece of apparatus called the ballistic pendulum. And basically, it's going to require knowledge of conservation of momentum and conservation of mechanical energy. So I'm going to start the lab by reviewing momentum and then conservation of total momentum. We will also review the two types of energy that we're going to need, kinetic and gravitational potential energy. And then I want to derive the equations that we will need for this lab, like specifically for the ballistic pendulum, okay? So let me start by reviewing the concepts of momentum and energy. Okay, so let me start by reminding you of what linear momentum is. And at first, we'll just look at a single particle, and then we'll look at a system of particles or a system of objects. So this is linear momentum of a single particle or object. Okay, so let's say I have some object. I'll draw as a square. Let's assume it has a mass m. And let's say it has a velocity in this direction, right? So remember, velocity is a vector. So remember, momentum, which is also a vector, usually call it P, is defined as the mass times the velocity. So the momentum, again, which is a vector, it's going to have a direction. It's going to be in the same direction as the velocity of the object, right? Because the velocity is a vector, the mass here is just a scalar, it doesn't have a direction. So the direction of the velocity tells you the direction of the momentum. And then of course they have units. There's no special name for the unit. So in SI units, this is simply going to be kilograms, right? That would be the units of the mass times, and then velocity is meters per second. So kilograms times meters per second would be the units for momentum. There's no special name for that combination of units. So that's for a single object, right? What if we have a system of objects? So now I want to look at momentum of a system of objects. So let's say I have m1, it has a velocity in this direction, call it v1. Let's say I have m2, the velocity is maybe like this, v2. Then m3, let's say the velocity is like that. So this is v3. And then I'll do one more, say m4. Say the velocity is like this, v4. Okay, so my system, right, consists of those particles. In this case, there's 4 of them, but there could be any number of particles. And one thing we may want to calculate is what's called the total momentum of that system. So P total. So this is like the total momentum of the system. And the way that you compute that is you find the momentum of each object or each particle in the system, and you simply sum them all together, right? But remember, they're vectors, so really you're adding a bunch of vectors together. So in general, this would be m1 times v1, right? That's the momentum of the first object, plus m2 times v2, plus m3 times v3, and so on, all the way up to the last one, which I'll call mn times vn. Okay, in this case, n is 4, right? There's 4 objects in our system. But in general, there could be n objects, right? It could be millions, actually. It could be any number of objects. So if we add up each individual momenta and add them all together, that's going to be the momentum of the total of the system, the total momentum of the system. Okay, now, what about this idea of conservation of total momentum? Well, this actually comes from Newton's second law. Okay, so let me jump to a new page here. So first, let me write Newton's second law for a system because it's a little bit different. So Newton's second law for a system. So what it says is that the net force acting on the system is equal to the total mass of the system. So if I add up all the masses of all the objects in the system, that would be the total mass. Let me write total mass here. Times the acceleration of the center of mass of the system. So this is really the acceleration of the center of mass. Okay, but it turns out there's another way you can write this equation. I could also write it as F net. Here, I'll do it using calculus notation first, but I know that all of you haven't seen calculus before, but let me start with that. So it turns out it's equal to the time derivative of the total momentum. So dp dt. Now, if you haven't seen calculus before, you can think of this as like the change in the total momentum divided by the change in time. Okay, so instead of that derivative with respect to time, think of it just as change in total momentum with respect to change in time. To get the derivative, what really happens is the delta t is getting smaller and smaller and smaller. We're taking the limit as delta t goes to 0. But for now, you can just think of it as that ratio, that change. So here's the key point. If the net force on your system of objects is 0, right? So if there are no external forces acting on the system, or if they sum to 0, right? So if there's no net external force acting on the system, so I'll put i.e. there is no net external force acting on the system. Now, internal to the system, that's okay, right? The objects can collide, bounce off of one another. There can be forces applied internally to the system. And it turns out those forces are going to basically cancel out. They're going to add to zero because of Newton's third law. Okay, so when I say the F net is equal to zero, I mean there's no net external force acting on the system. So if that's true, right, if you look at the equation here, if F net is zero, remember F net is equal to delta P total over delta T. So if I have F net equal to zero, that's equal to delta P total over delta T. Well, I can multiply both sides by delta T, right? So basically I'm going to get 0 times delta T is equal to change in P total over delta T times delta T. These cancel. Of course, 0 times delta T is 0. So what this is saying is that if the net external force acting on the system is 0, that the change in total momentum is 0. But remember, change in total momentum means like final total momentum minus initial, right? I could write this as, this really means P total final minus P total initial. That's equal to 0. If I bring the initial term to the right-hand side, I can write this as P total final is equal to P total initial. So this is what we mean when we say total momentum is conserved, right? The final momentum is equal to the initial momentum. Total momentum is conserved. Okay. All right, a little more review. Let's review a little bit about the two types of energy that we're going to need to compute. So remember, one type of energy is the translational kinetic energy. And basically, remember, this is energy due to the motion of the object. And actually, in particular, we're just focusing on translational kinetic energy. There's also something called rotational kinetic energy. You can kind of split it up. The translational kinetic energy is really due to the motion of the center of mass of the object. And we know this, right? Remember, people usually call it K or KE, depends on the book. In lab, I probably will call it KE, but I'll use both notations here. And remember, it's simply to compute it, it's 1/2 times the mass of the object times the velocity squared. Okay, and that's in the units of joules. Right, it's kilograms times meters per second times meters per second, but that combination of units we call a joule. And then gravitational potential energy that's energy associated with the Earth and an object, the system of the Earth and the object. So associated with the Earth object system. And remember that formula, some people call this U sub G for the U for potential, G meaning gravitational, or in this lab, I'll just use like PE, potential energy. Remember, it's equal to the mass of the object times G times some distance above a reference point, right? So the Y here is the vertical distance relative to some reference point. Okay, and then the mechanical energy is the sum of the kinetic and potential energy. So we could say, usually I call mechanical energy ME. So mechanical energy is going to be the kinetic energy plus the potential energy. And here's the key point about mechanical energy. It's conserved, right? So mechanical energy will stay the same, it's conserved, if there are no non-conservative forces like friction acting on the system. So mechanical energy is conserved if there are no what's called non-conservative forces. A big example of that is friction. If there's friction acting, you definitely don't have conservation of mechanical energy. So mechanical energy is conserved if there are no non-conservative forces like friction acting on the system. So then we would say basically like ME initial equals ME final. Or if I split it up, I could write this as KE initial plus PE initial equals KE final plus PE final, right? So mechanical energy is conserved. Just like in the last lab where we had the Pasco car going up the ramp, right? Since we said friction was negligible, so basically mechanical energy was conserved in that situation. Another thing I should also mention here is that if you have a system of multiple objects, then you could say that the total kinetic energy of the system, call it KE total for the system, is equal to the sum of the kinetic energies of each object in the system. So I'll write this as like KE1 plus KE2 and so on, right up to KE for the nth object. And same thing with gravitational potential energy. So potential energy total for a system be the potential energy for the first object plus the potential energy for the second object and so on. Now, in our case, in this particular lab, we are going to have conservation of mechanical energy only after the ball embeds itself in the pendulum. So the pendulum and ball are basically going to act as one single object. Okay, so we won't really have a system when we at least when we talk about conservation of mechanical energy. Okay, so the next thing I want to do, let me jump back to the handout first, and then we're going to actually derive the equations that we're going to need to ultimately calculate the velocity of the ball as it leaves the gun. So let me jump back. Okay, so I'm back to the lab. Again, I went over all this review, conservation of momentum, conservation of total momentum, talked about kinetic energy, gravitational potential energy, and mechanical energy. Okay, so now let's apply those theories to our situation, which is the ballistic pendulum. So what's going on with the ballistic pendulum? Actually, let me go back to the first picture. So we have this gun, and you guys should really watch the video on how I collected this data. We have this gun. It's going to launch a ball right out of the gun at some velocity. The ball is going to embed itself into the pendulum, and then the pendulum is going to rise to a certain height, right? Or you can also think of it, it's going to undergo a certain angular displacement, right? So it's going to rise by a certain angle. Based on that information, like how far it rises, and then the mass of the pendulum, mass of the ball, ultimately what we want to calculate is the velocity of the ball as it leaves the gun, right? So ultimately that's our goal, figure out the velocity of the ball as it leaves the gun. Now, why do we have to worry about conservation of momentum and conservation of energy? Well, it turns out when the ball collides with the pendulum, basically there are no net external forces acting, right? They're only internal to the system. If we consider the ball and the pendulum as our system, then the only forces acting are the force that the ball exerts on the pendulum and the force that the pendulum exerts on the ball. Well, due to Newton's third law, right, those forces are going to be equal and opposite, right? Equal magnitude, opposite direction. So they're going to sum to zero. They're like internal to the system. There's no other net external forces acting. We have obviously a force, a tension here in the rod, but we also have a weight, and those balance each other out, right? So we can ignore those. They sum to zero. So right during the collision, like before and after the collision, we can say that momentum, total momentum of that system of the ball and the pendulum is conserved. Actually, that's better seen in this picture right here. So this is our system, right? Again, the ball will apply a force to the pendulum will apply a force back to the ball, but that's internal to the system. They sum to zero. So this is right before the collision. And this is the case, the ball embeds itself into the pendulum. This is right after the collision. So now the pendulum and the ball are going to move off with a velocity we call now capital V. So before, the pendulum was at rest and the ball leaves the gun at V naught. So during this collision, we can say momentum is conserved, right? So the momentum before the collision should equal the momentum right after the collision. Okay, then what happens? Well, now the ball and the pendulum together will rise to a peak height, right? So here they have some kinetic energy, right? 1/2 mv squared, where v is the capital V here. They have some potential energy. Let's say we're using the lab bench as our reference point. So there's a height that the center of mass is above the table. So if I calculate m times g times h, right, h initial, that's going to be my initial potential energy. At the highest point, the kinetic energy is zero because it's at rest, or really, if we're being careful, we shouldn't say at rest. We should say its velocity is instantaneously zero, right, at the highest point. But it has even more potential energy, right, because the height is larger here. So if I sum the kinetic and potential at the initial position, and I sum the kinetic and potential at the highest position, which is really all just potential because the kinetic is zero, then that gives me mechanical energy. And remember, since there's no friction, there's no non-conservative forces acting, mechanical energy should be conserved. So what that's going to allow me to do is to solve for this capital V, to find this velocity V. And then finally, I can figure out that maximum height, right? Really what I want is the difference in height between the final position and the initial position. So this delta H, I can figure that out by looking at the length of the pendulum and then the angle it undergoes. So that's sort of the angular displacement theta that the pendulum swings up, that it undergoes. So using that information, I can figure out delta H. And then I can work backwards, and ultimately I can calculate the velocity of the ball as it leaves the gun, okay? So let me show you all of this. I'll go back to the iPad to derive this. Okay, so let me first draw what happens before the collision. So before the collision, and then later I'll draw what happens after the collision, meaning right before the collision and right after the collision. So before the collision, right, I have this ball that leaves the gun. It has a certain mass, m1, and we know it has a velocity that leaves the gun at a v naught, call it v naught. And then the pendulum here has a mass m2, and it's at rest, right? So it's at rest right before the collision. And then after the collision, the ball embeds itself into the pendulum. So you can think of it as like a ball pendulum combination. Actually, now the mass is going to be m1 plus m2, right? Because think of them combined now. And it's going to have a velocity, which we're going to call capital V, right after the collision. Okay, so if I consider the ball and the pendulum to be my system, this is the system before the collision, and this is the system after the collision. I'm going to use my standard coordinate system, right, where I have x to the right and y vertical. So x to the right and y in the vertical direction. Okay, so we know, again, I explained earlier that there's no net external forces acting on that system, right, during the collision. They're all internal forces. So therefore, momentum, at least in the x direction, and we only care about the x direction in this case, momentum in the x direction should be conserved. So what I can do is I can calculate, I'll call it P total, the momentum of the system, initial in the x direction, and then P total final, final meaning right after the collision in the x direction. Well, initially, it's going to be the momentum of the ball, which is m1 times v naught. Right now, I'm not even using vectors because I'm just talking about the x direction. It's positive v naught. And then plus, remember the momentum of the pendulum is going to be mv, but now the m is m2 and the velocity is 0, right? It's at rest. And that should equal, remember, this should be conserved. So that should equal the total momentum in the x direction after the collision. Well, now the mass is m1 plus m2 times capital V, right? Because they're moving together with that same velocity, capital V. So what I can do here is I can solve this for V naught, right? So I have, again, m1 V naught is equal to m1 plus m2 times V. So let me divide both sides by m1, right? These cancel. So I have V naught is equal to m1 plus m2 times capital V divided by m1. Okay, great. So that's my first really important equation. I'll box it. Okay, now I need to figure out capital V. Well, I get that by recognizing that I have conservation of mechanical energy for the second part, when the pendulum actually rises to a peak height. So in the second part here, actually, let me do a new page. So now let's say this is the lab bench. Right here is the pendulum and ball combination. It's at some initial height, right? H initial. It has some initial velocity, remember it's capital V. And then it's going to rise to like a peak height. Let's say it's right here. And it undergoes an angular displacement of theta. Okay, so this is like H final. And then this difference in height, I can call that delta H. Right, so that's basically H final minus H initial. Is delta H. And what's true about the pendulum and the ball, that combination at the highest point, it's at again, really, I should say, I want to say at rest, but I'll say the velocity is 0. Just for an instant. I'll say at highest point. Okay, now because I have no non-conservative forces, like there's no friction in the pin, we're assuming it's pretty much frictionless. Of course, it's not exactly, but pretty much frictionless. So therefore, mechanical energy should be conserved, right, when it rises to the peak height. So that means the mechanical energy initial, right after the ball embeds itself and it's moving with that velocity v, should equal the mechanical energy final when it's at the ball and pendulum combination or at the peak height. But remember, mechanical energy is kinetic energy initial plus potential initial. That's going to equal kinetic energy final plus potential energy final. Okay, so what is the initial kinetic energy? Well, it's 1/2 times the mass, but they're moving together, so I can add these together, times v, it's capital V squared, plus the initial potential energy is m, but it's the total mass, right, times g times h initial. And that's got to equal kinetic energy final, which is 0, plus potential energy final, which is m1 plus m2 times g times h final. Okay, so now what I want to do is I want to solve this for capital V, okay? So first thing I could do is I could divide everything. First of all, I could divide everything by m1 plus m2, right? So these basically cancel. Then I can multiply everything by 2, right? I'll do that carefully. So 2 times 1/2 v squared plus 2 times gh initial equals 2 times gh final, right? So this is going to be v squared plus 2gh initial equals 2gh final. Now let me bring this 2gh initial to the right-hand side, so I need to subtract it from both sides. So I have v squared equals 2gh final minus 2gh initial. I can factor out a 2g, so I'm left with h final minus h initial, but we called that delta h, right? So this is 2g delta h. And then finally, I can take the square root of both sides. It doesn't make sense to take the negative root, so I'm just going to take the positive root. So it should be square root of 2g delta h. Okay, so that's like the second really important equation. And now I really want to figure out what delta h is, because I can't really measure the height difference from the table. It turns out it's very small. It's like, around 3 millimeters, maybe a little less than 3 millimeters, so like 0.003 meters. So it's very, very, very small. So the best way to figure this out is to use the angle, right? The angular displacement of the pendulum. So here, let me derive that. So one last thing we need to figure out. We need to figure out delta H based on the angle. So in this case, I have my pendulum and the ball. It swings up to some height. I'll say right here. We know, and this is the angle theta, right? That's theta. We know the length of this. So I'll give you that value. We can measure it. And of course, that's the same as this length right here. Doesn't matter if it's swung up, right? It's still the same length. And the delta H, the change in height, is going to be this distance right here, right from here to here. Okay, so how do I figure out that? Well, one thing, I could figure out this distance, right, from here to here, because that's got to be L times cosine of theta, right? I can use my trigonometry. So this is simply going to be L cosine of theta, right? It's adjacent to the angle. L was the hypotenuse, right? So it's L cosine theta. So therefore, if you want, you can think of it as this total length here, this total length from here to here, this L, consists of L cosine theta plus delta H. Here, let me write it out in steps. So I have L cosine theta plus delta H. That's got to equal the total length, right, of the pendulum. So now let me solve this for delta H. So I'll subtract L cosine theta from both sides. So I have delta H is equal to L minus L cosine theta. And then of course you could factor out the L. So if I take out L, I'm going to be left with 1 minus cosine theta. So let me box that. Okay, so the point here is if I know the length of the pendulum and I know the angle that it rose to, I can calculate delta H. If I know delta H, let me go back here, I can plug it in here and I can calculate capital V, the velocity right after the collision. If I know capital V, I go back here, plug it in here. I also have to know the mass of the ball and the pendulum, okay, which we can figure out. That will allow me to find the velocity of the ball. Right, so this is going to be like the predicted velocity of the ball. I'll call it launch velocity. So it's predicted by using both conservation of total momentum and conservation of mechanical energy. Okay, so let me go to the handout now. Okay, so we derived all the formulas that we need, right? So let's look at the experiment. Again, if you have a few minutes, it's a really good idea just to watch this quick little video on how I collected data, like what the equipment actually looks like and how I collected the actual data. Okay, first part of the experiment. We want to measure V naught another way as well. We want to experimentally measure V naught. Well, how do we do this? This is done exactly the same way we did this in the projectile motion lab, where we launched the ball horizontally. It landed, in this case, it landed on a piece of white paper with carbon paper on top, so it leaves a mark. If I measure the displacement, right, and I measure the height of the gun, then that gives me enough information to figure out the velocity, right, the launch velocity. Okay, so first table. This is basically the horizontal displacement, how far from the bottom of the gun horizontally it landed. So this is in meters. We're going to use SI units for this part. So question one, I want you to determine the average horizontal displacement and then the percent experimental accuracy for the horizontal displacement. Okay, make sure again you round the average to 3 decimal places. Then you can find all your absolute deviations. I'll round it to 3 decimal places. You can find the average absolute deviation to 3 decimal places. And remember, the accuracy is always the average absolute deviation divided by the average displacement times 100. And then for the height of the gun, I did 5 trials, but basically I got the same value. So I just average those. And of course, you're going to get 0.162 meters. Okay, and make sure you show me the calculation, right, for this percent accuracy. All right, now using kinematics, right, and we've already used this equation. Actually, we used this when we did the projectile motion lab. The launch velocity, we're going to call this the experimental launch velocity, is simply going to be delta x over delta t. Well, delta t is like the square root of 2h over g. So if I flip it, then I have delta x times the square root of g over 2h. So that should give us the experimental launch velocity. Okay, so again, delta x is going to be your average here. G is 9.8, and then the h is 0.162. Okay, so show me that calculation. That'll go here. That's the experimental initial speed of the ball, right? The launch velocity. Okay, then I used, here's where I actually fired the ball into the pendulum and I measured the angle, how far it went up, and I did 10 trials. Turns out I got the same value for all 10. Okay, that's fine. So I want you to average them. Obviously, you're going to get 8.5. Since it turned out that the resolution of the instrument, the finest I could read that scale, the angle scale, was 0.5 degrees. That means that basically, I want you to compute the percent accuracy, but basically all these absolute deviations are going to be 0. But then you have to argue for the average absolute deviation here, I have to use at least the resolution of the instrument, which is 0.5. So everyone's going to get the same thing here. You're going to get 0.5 divided by 8.5 times 100, and that'll be your percent accuracy. Right? And again, show me that calculation. Okay, then I remove the pendulum so I can measure the length. That's in this table, so 0.297 meters. I measured the mass of the ball and the mass of the pendulum. So question 4 is simply calculate the change in height, right, in meters. It's going to be a very small value. Right? Remember, the equation is L times 1 minus cosine of your average angle, cosine of 8.5. Make sure your calculator is in degrees, right, when you do this calculation. Okay, I also want you to estimate the percent experimental accuracy for the masses. Well, since we only massed it once, right, we didn't do a bunch of different trials. The way that we can estimate this is we can assume that the accuracy is going to be the resolution of the instrument divided by your average mass, which is your one mass value here, times 100. And the resolution of that scale was 0.1 grams, which is the same as 0.0001 kilograms, right? So like this value right here is simply going to be 0.0001 divided by 0.0098 times 100, right? So you're just you're estimating those percent accuracies. And again, show me those two calculations. Okay, now that we have delta H, right, we can compute V. Remember, that was a velocity right after the ball collided with the pendulum and embedded itself in the pendulum, right? And they moved together with that velocity V. So calculate capital V here. Then once we have capital V, right, and we know the masses, remember M1 is the mass of the ball, M2 is the mass of the pendulum, right? Those masses are given here. You can calculate what we really want to get is the velocity, the launch velocity or initial speed right after it's launched. So V naught, and we're calling that V naught predicted, right? So that'll go in here. Question 8, compare the two values for V naught. So V naught experimental, remember that was calculated back in question 2 to V naught predicted, which is from question 7. So compare them by calculating the usual percent experimental error. So make sure you divide by the predicted one. Okay, then I want you to calculate the total kinetic energy of the system right before the collision. Well, because the pendulum is not moving, it's at rest right before the collision, the kinetic energy is simply going to be the kinetic energy of the ball, right? The total kinetic energy of the system is simply going to be the kinetic energy of the ball. So the total kinetic energy of the system right before the collision is going to be 1/2 the mass of the ball times, and we're going to use V naught predicted squared. Don't use your experimental, use your predicted one. Now compute the final kinetic energy immediately after the collision. So now the mass is the total mass, right? Because they're moving together, the mass of the ball plus the mass of the pendulum. So it's 1/2 times that total mass times capital V squared. And that'll be the final kinetic energy right after collision. So this is the kinetic energy of the system right before the collision, final kinetic energy right after the collision. Now here's the thing, and I'm not sure how much by this point you have talked about in lecture, but this is what's called a completely inelastic collision, because the ball collides with the pendulum and then they move together as a unit, right? It doesn't bounce off or anything. So it turns out if that's the case, then some of that kinetic energy is being transformed into another form of energy, because we know ultimately energy is always conserved, like total energy is always conserved. And it turns out that most of that energy is being transformed into heat, right? Or it's really called thermal energy. Some people say like some of that kinetic energy, some of the initial kinetic energy was lost, right? But really it's not lost, it's transformed into another form, in this case, thermal energy. So what you should find is that your initial kinetic energy here is larger than the final kinetic energy, right? Some of it is missing because it's turned into this thermal energy, right? Heat, some people call it heat. So what I want you to do for the last question here is calculate the percentage of the energy, and I have it in quotes, lost. So it's simply going to be the kinetic energy initial minus kinetic energy final divided by the kinetic energy initial, right, times 100. Okay, it's just like a percent change. So kinetic energy initial minus kinetic energy final divided by kinetic energy initial times 100. And you should find it's quite a large value. Like a lot of that kinetic energy is lost from the collision. So we can't measure it, but if you were able to measure the temperature of the ball and the temperature of the pendulum after the collision, you would find that the temperature has risen a little bit. Like the atoms are going to be vibrating a little bit more. Okay, and then that's it. So pretty straightforward lab. It's interesting because it verifies our theories, right? Conservation of momentum and conservation of mechanical energy. Great, thank you.